Hey, good morning everybody. This is Mr. Ainsworth and we're going to get into section 5 here and talk about how to solve trigonometric functions with multiple solutions due to a change in period. We're going to also do it graphically and as well as algebraically. But before we do, let's go above here and let's review what we did in the last lesson. In the last lesson we did two things. We learned how to simplify complicated expressions and we learned how to prove certain things. So let's get into it. One of the first things that we did was we rewrote the expressions in terms of sine and cosine. And we know that here that cosecant A is the same thing as 1 divided by sine A minus cosine A times cotangent A, which is cosine A divided by sine A. That we do know. We know that cosine A times cosine A is nothing more than cosine squared A. So we have 1 divided by sine A minus cosine squared A, okay, cosine squared A divided by sine A. And one of the things I also said in the previous lessons is that you need to combine fractions. And since these two have the same denominators here, we just take the numerators, which is 1 minus cosine squared A, and write it as a single fraction. So we have 1 minus cosine squared A divided by sine A. And then you got to be thinking, okay, can this be simplified further? Is there identity for the numerator? And I'm talking about this. And you got to be thinking, okay, 1 minus cosine squared A is what? And you got to say, Ainsworth, I know what that is. It is sine squared A. We know that there's a Pythagorean identity right here. So this becomes sine squared A here. We're going to substitute that in, divided by sine A. One of the signs upstairs cancels out with the denominator here, and you get sine A, okay? And that ends the first one there. The second one is sine squared divided by 1 plus cosine, sine squared theta divided by 1 plus cosine theta. And what we need to do is simplify this one. Now, we do know that a squared function here, anytime you see either cosine squared or sine squared, you have an identity for it. And I do know, I love saying that, we know that sine squared theta equals 1 minus cosine squared theta from the Pythagorean identity. So I'm going to make a substitution, and the reason why is because I know this is factorable. In my previous lessons I said that 1 minus cosine squared theta is factorable into 1 plus cosine times 1 minus cosine. And I see that there's 1 plus cosine theta downstairs. So what I need to do is substitute this in, write down what this is equal to, and then divide that by 1 plus cosine theta. Don't even dare try to cancel out one of these cosines because that's an illegal move right here. So don't do that. That'll be definitely an illegal move. What you want to do is you want to factor this. Okay? So we're going to factor the difference of squares here as 1 plus cosine theta times 1 minus cosine theta. The difference of squares. In the previous lessons I said that a squared minus b squared equals a minus b times a plus b from algebra 1. It's called the difference of squares. Okay, so we're going to use that again. Over here, a 1 minus cosine squared theta is the difference of squares. You factor it, boom, you're good to go. Divide that by 1 plus cosine theta. Notice that these are equal, they cancel to 1, and you get something very, very simple. You get 1 minus cosine theta. And that's how you do number 2. Now number 3 is a proof. And when you do a proof, you start off with a more complicated side, and typically it's the left side. Not always, but typically. And what I'm going to do is I'm going to start off with it. So 1 minus sine squared theta divided by 1 plus cotangent squared theta. And I'm going to go through a series of equalities, and I'm going to show that it's equal to the right-hand side, which is sine squared theta times cosine squared theta. I always put my goal down here down low, so I know what to shoot for. I start off with the left side. Okay, this is the left side. And I have to prove that it's equal to the right side. If I do that through a series of equalities, I can use the transitive property and prove that the left is equal to the right. So here we go. I know that I have an identity for up top here, and I know that 1 minus sine squared theta is nothing more than cosine squared theta. Anytime you see squared functions, think Pythagorean identities. Think those first 3 basic ones that I went over in the first lesson, okay? Well, a couple lessons ago. And I know that 1 plus cotangent squared theta is nothing more than cosecant squared theta. Two identities right there in the same fraction. Okay? Now, cosine squared theta is 1 over sine squared theta. So we are going to do a little substitution here. I'm going to take cosine squared theta in the numerator, divide it by cosecant squared theta, which is 1 over sine squared theta. And as I always do, when I deal with complicated fractions here, is I multiply by the reciprocal. So from here to here, I want to multiply by the reciprocal, do a basic fraction technique here. I'm going to take cosine squared theta times the reciprocal of 1 over sine squared theta, which is just sine squared theta, and I'm done. Notice that it's my right-hand side. So these two are equal, of course, because the order of multiplication doesn't matter. All right, it's called commutative property. I can switch the order here, and I get it. And when you're good and you get it correct, you get happy and say QED, quad eris demonstratum. Okay, Latin. Quad eris demonstratum, which means that which was to be demonstrated, okay? Back in the, believe it or not, the Greek times, 600 years before Christ. I don't know if they knew trig, but, you know, they knew that right there. Okay, that was the previous lesson. Let's get right into the new lesson here. Let's go into 8.5, and let's solve now trig equations that are a little bit more complicated. First algebraically, well, and then graphically as well. In fact, you know what, this one here, I'm going to solve it graphically first. Okay? Now to do that, you want to isolate the sine function. So what we want to do is we want to take this over here, and well, I'll tell you what, we'll work on it algebraically first. Okay, so we have 2 sine squared theta, excuse me, not theta, x, 2 sine squared x, where x is your angle here, minus 1 equals 0. And I want to solve it in radians, so our answers are in radians right here. Answers in radians, because it's 2 pi, not 360 degrees. So we're going to do it in radians. Okay, and we're going to do it algebraically. So what I need to do is just do some simple algebra. I'm going to add 1 and divide by 2. And I get sine squared x is equal to 1/2. The inverse of squaring is rooting, so I need to square root both sides. So here and here. And I get sine x, is equal to plus or minus now. You got two solutions here. The square root of 1, which is 1, divided by the square root of 2, which we know, after you rationalize it, right here, let's rationalize it, gives us sine x is equal to plus or minus root 2 divided by 2. Now, this is a nice ratio. That's on your 45, 45, 90. Okay, and you know that the sine of 45 degrees, or in radians, pi fourths, gives you this ratio. But we actually have to solve there's two equations here. When sine x equals positive root 2 over 2, we're looking at quadrants 1 and 2, because sine's positive there. When sine's negative, you're looking for quadrants 3 and 4. So basically, we're looking for all 4 quadrants. Solutions, okay, in all, okay, 4 quadrants. So it is actually easier than it looks. We know we started quadrant 1 with a 45 degree angle, or a 45, or pi 4, excuse me. All right, so my solutions in all 4 quadrants, in quadrant 1 is pi fourths, that's quadrant 1. Quadrant 2, okay, you have to take pi minus that, which is 3 pi fourths. You can look on the unit circle to verify all this. And then quadrant 3, you take either, you can add, well, to get quadrant 3, you add pi to pi fourths, you get 5 pi fourths. All right, basically it looks like this right here. So pi fourths here, 3 pi fourths here, and then you get 5 pi fourths here, and then 7 pi fourths here in quadrants 1, 2, 3, and 4. And then in quadrant 4, of course, you get the 7 pi fourths. And the reason why is because of this right here. When sine's positive, you have quadrants 1 and 2. When sine's negative, you get 3 and 4. So we're looking for solutions in all 4 quadrants. Remember that. Now, how do you see that on the graph? Okay, so let's do this. Let's take a look at our equation here. Let me rewrite it again over here. Sine x is equal to plus or minus root 2 over 2, and let's call this y1 and this y2. So my first equation is y1, sine x. My second equation is root 2, or plus or minus root 2 over 2 here, which is about 1.4 divided by 2, or about 0.7, plus or minus, that is. Well, I'll tell you what, let me take off this right here. I can say that, well, okay, I'll just call it y2, so plus or minus 0.7. So we have two horizontal lines, one at 0.7, one at negative 0.7. So two horizontal lines here. So the very first thing you do is you graph it. Okay, so here we go. Scale the axes. Let's go out 1, 2, 3, 4. Call that 2 pi, and this pi here. And let's plot our sine function first. Now this is a skill you learned in the last chapter, so you need to be able to graph these functions quickly. And to do that, you do the graphing drill that I gave you guys. Now 0.7 is a little under 1. So the next thing we do is we graph two horizontal lines, one at 0.7, which is about here, and the other one, which is about here. And notice something here. We have y equals root 2 over 2, which is positive 0.7. We have y equals negative root 2 over 2, which is negative 0.7 here. We have four solutions. Intersects here at x1. That's between 0 and pi halves. That's quadrant 1. We have another one in quadrant 2. That's x2. We have another one here, quadrant 3. That's x3. And we have another one here, and we have that in quadrant 4. That's x4. So this is pi force. Okay, right here. This is x2 is 3 pi force. And then we have 5 pi force here. And then we have here 7 pi force here. Those are the solutions. And so the graph backs up what we have over here algebraically. I concluded that we have four solutions here. The graph backs that up. And if you graph these on the on your TI-84, so graph on the TI-84 or something similar to check. Okay? You're going to enter in three functions. y1 is your sine function, y2 is the positive one here, and y3 is your negative one. Okay, don't enter in 0.7, enter in root 2 divided by 2 to be exact, and negative root 2 divided by 2 to be exact. You're going to see the same graph. Set your x minimum right here. This is your x minimum. X min equals 0. And then this would be your x max right here. And then this would be your y max would be 1. And your y minimum would be negative 1. That's in your window setting. So you need to do that. Get used to changing your window settings, and so you can see what I'm seeing. Okay? Make sure you do that. Now they're not all that easy, so let's get into some more fun equations here. And let's do them. Let's solve them algebraically here. So on this next one here, on number 2, we're going to take a look at cosine squared x minus 3 cosine x minus 4 equals 0. And let me bring it over here so I can work on it. Cosine squared x minus 3 cosine x minus 4 equals 0. And this is called a quadratic. Okay, anytime you have degree 2, okay, degree 2, that represents a quadratic. And that should sound familiar because in Algebra 2 you studied these extensively. In fact, this is the same as x squared minus 3x minus 4 equals 0. So let's recall something from Algebra 2. We have, when we're solving x squared minus 3x, this is minus 3x here, just taking away cosine here, minus 4 equals 0, the very first thing your teacher said last year was to factor, if possible. And so you try to factor into two binomials. And you write x times x will give you the first term, and factors of, let's say, negative 4 that added a negative 3 are like, well, try negative 4 and positive 1. Negative 4 times 1 is negative 4, but negative 4 plus 1 is negative 3. And so it's factorable. And then your teacher said, hey, what are the zeros to this? And right here, 4 minus 4 is 0, so x equals 4 is a solution. And right here, x equals 1, negative 1 is a solution as well. And so these are roots or solutions to the quadratic equation. Well, the same is true over here, but instead of x, I have cosine x. So when you factor it as cosine x. Okay? Instead of x times x, you have cosine x times cosine x will give you that first term. And then factors of negative 4 that add to negative 3 are, again, minus 4 and a positive 1. And that's equal to 0, of course, because it says so up here. And then you solve each. Now, I'm going to set each equal to 0. That's what you did right here. And technically, you went x minus 4 equals 0, and you got 4. And you went x plus 1 equals 0, and you got negative 1. So here you do the same thing. You go cosine x minus 4 equals 0, and you solve that. And then you go cosine x plus 1 equals 0, and you solve that, and you get some solutions. They're obviously not going to be 4 and negative 1. They're going to be something else because we're not dealing with x, we're dealing with cosine x. Okay, now you isolate your function here. You get cosine x equals 4. This right here is out of range. What that means is that we know that cosine x is bounded between negative 1 and 1, and this is 4, obviously, beyond 1, and it's out of the range, which means, all right, there's no solution. That's what this means. So when this is out of the range, it's greater than 1. Greater than 1, there's no solution here. That's what out of the range, or what I'm talking about, means. Over here on the right, we have something different. We have cosine x equals negative 1. When is cosine equal to negative 1? And the answer is when x equals pi, okay, on the right side, left side of the unit circle. And so really, believe it or not, this fancy equation here only has one solution, and we found it, x equals pi. Okay? Okay. Excuse me. Well, plus technically it's actually plus multiples of 2n pi, but let's say that we're finding all x such that 0 less than x, or less than equal to x less than 2 pi. So all solutions less than 2 pi. So we only have one solution here. Only one solution. Okay, and on the third one here, we want to do something similar, but we got a little extra challenge. And this one here shows you a little bit different thing that you're going to be encountering in your homework here. Notice we have 2 sine x minus sine x equals cosine squared x. We have two different functions. No good. You don't want two different functions. You want one function only. So let's write that down. Okay? You want one function only. One. So what we have to do is we get creative here, and we have to rewrite this equation in terms of one function only. Okay. So what I'm going to do is I'm going to take this and I'm going to substitute in its equal. And we know, there we go again, I love saying that. We know that cosine squared theta, or x here, is equal to 1 minus sine squared x. So what I can do is I can replace that with what it's equal to. So I'm going to take my equation here. I'm going to say that 2 sine squared x minus sine x is equal to whatever this is equal to here. Okay, we know that what I said was that cosine squared x equals 1 minus sine squared x. So I'm going to substitute that in. 1 minus sine squared x. And now I have an equation in terms of one function only. Everything is involved in sine. And then I'm going to set it equal to 0 and see what happens. So from here to here, I'm going to set it equal to 0 because that's how you deal with quadratics, and try to factor it and use some similar techniques. So I'm going to subtract the 1, and I'm going to add the sine squared x. So I add the sine squared x to 2 sine squared x, and I get 3 sine squared x minus sine x here, minus the 1, of course, equal to 0. Okay, so I set it equal to 0, and then right here, again, I want to try to factor it. Okay, now this equation is like 3x squared minus x minus 1. 3x squared minus x minus 1 equals 0. That's what you saw last year in Algebra 1. And you factored it into binomials like you did. 3x times x is 3x squared with the factors of 1 in. And you try to factor it. But factors of negative 1 that add to negative 1, it's impossible. It's not factorable. Okay, so this is not factorable either. So then, hey, you learned other ways to handle this. You learned the quadratic formula, okay? So what we're going to have to do is we're going to have to take this and we're going to have to use the quadratic formula to handle this. Okay, fun stuff. So you have to remember that. And the quadratic formula, as you guys know, is negative b plus or minus the square root b squared minus 4ac, all divided by 2a. That's the quadratic formula. Okay, now to use the quadratic formula, you need the coefficients. Okay, negative or 3, negative 1, and negative 1 again. So A is negative 3, B is negative 1, A is 3, B is negative 1, C is negative 1. Let's write that down. A equals 3, B equals negative 1, C equals negative 1. But instead of saying, x equals this, like in the typical quadratic equation that you experienced last year, we have sine x. So that's what you start with. So you say sine x, not x, because their equation is in terms of sine x, not x, is equal to the opposite of b, which is the opposite of negative 1, which is 1, plus or minus the square root of b squared. You get square negative 1, you get 1, minus 4 times a times c, all divided by 2 times a, which is 3. So sine x, what does that equal? It's equal to 1 plus or minus the square root of 1 plus 12, which is 13. So you get root 13 here, all divided by 6. Okay, so let me clean that up here. There we go. All right, so what do we have? What is this telling us here? One of the equations is sine x is equal to 1 plus the root 13, all divided by 6. Or you have sine x is going to be equal to 1 minus root 13, all divided by 6. And you have two equations here which you have to solve. So this obviously calls for the calculator, so let's get one going. Okay, so what we need to do is we need to figure out this value. Now this is a positive number here, and sine's positive in quadrants 1 and 2, so we're looking for a quadrant 1 and a quadrant 2 answer. And when you put this in the calculator, remember that it's important to use parentheses around the numerator, this binomial here and here. Just remember that, otherwise you're not going to get the right value. So in your calculator here, what we want to do is take the inverse sine of this number here. That's your first solution. X is equal to the inverse sine of 1 plus root 13 divided by 6, whatever that is. And remember, let me put these in blue, you have to have parentheses around your numerator. So you're going to have to double up. So here we go. I'm going to take the inverse sine. Oh, you know what? Let me check if I'm in radians here. I am. Okay, so I need to take the inverse sine of the quantity. So you go left parentheses again. 1 plus the square root of 13, close it up, divided by 2. Divided by, oh, not 2, 6. Ooh, I got to fix that. All right, and then enter. And that's about 0.875. No, that's not correct. I got to have 6 inside the parentheses here. You know what? This is not correct. And you got to be careful how you use a calculator because it looks good, but it's really not. Watch this. Let me try it this way. I'm going to enter in the fraction first so I can eliminate some of the problems here. So the quantity of 1 plus the square root of 13. Okay, I got to close off the root. And now I've got to have the same number of right parentheses as left. So 2 on the left, 2 on the right. Divide that by 6 now. Okay, I get that. Now I have to go ahead and take the inverse sine. So inverse sine of that answer. So now I go recall, answer. Oh, I did it right. How about that? Okay, so that's cool. That's the first solution in quadrant 1. So 0.875. So let's write that down. So the first solution, x is equal to 0.875 radians. That's quadrant 1. Okay, now quadrant 2. Quadrant 2 is pi minus that. So what I need to do is to take pi, subtract my answer, so I recall it back, and that's my quadrant 2 answer, 2.267. So 2.267 radians. That's my quadrant 2. That's just for the first equation, and now I have to repeat that for this one over here. Okay, so let's go have some more fun over here. So let's do the same thing. Let's take 1 minus the square root. I got to put that in quantity here. So 1 minus the square root of 13. Divide that by 6. Okay, and I get negative 0.3 or negative 0.434. So x equals negative 0.434. Well, I got to correct this over here. This is divided by 6. The denominator is 6 right there. And that's quadrant 4. That's negative. So what I want to do is I want to reflect it up to quadrant 1. So that's my reference angle, 0.434. And I got to get to quadrants 3 and 4. Okay, so I need a quadrant 3 angle and I need a quadrant 4 angle here. So all I need to do is really, to get to quadrant 3, I just add 180 to that. Because if I reflect it up, I get 0.434 in quadrant 1. To get to quadrant 2, I got to subtract it from 180. So you might as well just take this negative number as it is and add pi to it. That's the fastest way to get to quadrant 3. Okay, so let's just add pi. Okay, and that will give us a 2.70. Okay, so 2.707. So 2.707. That's quadrant 3. Pi is about 3.4, so I know it's less than pi right here, radians. And therefore, it's a quadrant 3 angle there. And now I have to get to quadrant 4. Now, we know this negative angle here is already in quadrant 4, so all I have to do is go get a coterminal angle of that. And also, all I have to do is just simply add 2 pi to this. So what I'm going to do is I'm going to get it back. I'm going to get that back. So I'm going to redo the calculation. 1 minus the square root of 13 divided by 6. Whoa, what happened here? Oh, I put 2 division signs. Okay, can't do that. So 1 minus the square root of 13 divided by 6. I'm going to take, oh, you know what I forgot to do? I forgot to take the inverse sign. That's the problem here. I made a silly mistake. I got to take the inverse sign of that. Oh, silly me. I'm being distracted here. I got to take the inverse sign of that. Second answer. Okay. Oh, that's my angle. That's where it happened. Let me double check something. Okay, I was just double checking my calculations here. Negative 0.434 is just the fraction approximated as a decimal. I have to take the inverse sign of it. So inverse sign of my answer, and I get negative 0.449 radians. So this is actually in red here is actually equal to the sine x. I need to take the inverse sign of that. So what I need to do is just go ahead and clean this up a little bit and rewrite my numbers here because I was a little distracted earlier and I made a silly mistake. So let me fix this here. I know that after I take the inverse side of my fraction, which is negative 0.434 as a decimal here, I get the angle negative 0.449 radians. So my first angle here is negative 0.449 radians, but that's quadrant 4. Okay? So I need to go coterminal to that. I need to add 2 pi to that to get my quadrant 4 angle. So I add 2 pi on the calculator to get my quadrant 4 angle. So plus 2 pi. And I get 5.834. Okay? 5, x equals, what did it say? 5.834. 5.834 radians. That's quadrant 4. Now I haven't found my quadrant 3 angle yet. Let me write it down here. Remember, negative 0.449 radians is clockwise rotation in quadrant 4. To get a coterminal angle, you just add 2 pi, and I get 5.834 radians, which makes sense because I know that 2 pi radians is about 6.28. This is a little bit under 6.28, so I know it's quadrant 4. But what in the world is my quadrant 3? Well, I need to take my negative angle here in quadrant 4 and just add pi to it to jump to quadrant 3. Let's try that. Okay, so let me get it back. Let me take negative 0.4. I'm just going to read up here instead of redoing the calculation. 9 and then 214. Let's take some more digits. Okay, I'm going to add pi to that to get to quadrant 3. and I get about 2.692. So 2.692 radians right there. A little bit of a complicated example only because of the quadratic formula, number one, and number two, we're taking this complicated looking fraction here, and we have to take the inverse sign of it and jump to all four quadrants. Okay, so we have actually four solutions. We have here, this one, and we have these four solutions here. Crazy. All right, let's do something a little bit more manageable. Let's work on this one here. And I'm running out of room on the left, so I'm going to go to the right just for this time. This involves another technique. Whenever you notice the same function in common in an equation here, what you want to do is get everything to one side and factor it out. We used to call that in algebra, we call that factoring out to GCF. But the very first thing you do is you get everything on one side, like the left side here. And let's do that. Sine x times tangent x minus 3 sine x equals 0. So get everything on one side, subtract 3 sine x. And then whenever you see a common factor like sine x, factor it out. In fact, let's put that in red. This is a technique that's used all the time. Always. Factor out, okay, BGCF. Okay, so I'm going to do that. I'm going to take sine x here, multiply that by tan x minus 3, set that equal to 0. And this is a zero product. So either the first one has to be equal to 0 or the second one has to be equal to 0 for the product equals 0. You saw that in algebra as well. Okay? So sine x must be equal to 0, and the second one, tangent x minus 3, when is that equal to 0? Well, this one's a pretty easy one. We know that sine of pi is equal to 0, so x could be pi here. And then here we have to solve for tangent x, so we add 3 and shift it over here. And we get tangent x equals 3, and that's in the range of tangent because the range of tangent is all reals. And 3 is not on the special right triangles though, so this is a calculator problem. So x equals the inverse tangent of 3. And that's a positive number, so we're looking for quadrant 1 of 3 here. So we use our calculator again. We set it in radian mode because we're going from 0 to 2 pi here. We take the inverse tangent of 3, and we get 1.249. So 1.249 in quadrant 1. To get to quadrant 3, that's simple. You just add pi. So what we do is get the calculator again. Just go plus pi equals, and you get about 4.390. No, 4.391. So 4.391 radians in quadrant 3. So we really, in this one, have 3 solutions, here, here, and here. A little bit more simple. The previous example, number 3, you're not going to really have to deal with that much. I probably shouldn't have included that in my notes, but what the heck, man. You got to see the tough stuff once in a while. Most of your homework's going to be like number 4 here. All right, nothing too difficult. All right, last one, number 5. Let's do this one over here. 2 sine x equals cosine x. This is another type of equation. I picked this one here because it involves another technique. We have 2 different functions here, which is not good. And like I said, you want one function only. Okay, you want, one, function only. Now, the previous cases I showed you, I made some substitutions, but there's another way you can make that happen. And the way you can make it happen is get creative. You can just divide by cosine x here. And you say, hey, Ainsworth, why would you do that? Well, if you do that, we know that sine x divided by cosine x is tangent x. So really we have 2 tangent x is equal to 1. Okay, so now you have one function only. So dividing through by a function will allow that to happen. It's a new technique. That's why I put this example in here. Isolate your tangent function by dividing by 2 to get 1/2 here. 1/2 is not on the special right triangle, so this is a calculator problem. And tangent's positive. 1/2 is positive. So tangent's only positive in quadrants 1 and 3 again. So quadrant 1, quadrant 3, x is equal to the inverse tangent of 1/2. And that's a calculator problem, like I said. So you take the inverse tangent of 1 divided by 2, and that's about 0.64 radians. 0.64 radians. Oops, I didn't say that correctly. 0.46. 0.464 radians. Okay. And then my next one here, you just have to add pi to it. When it gets from 1 to 3, you always add pi, just like I showed you up here. Let's highlight that. And then, no, what do you have? So you go plus pi, and you hit the go button, 3.605. So 3.605 radians. So we have two solutions here, and we have this one here. Okay, so I showed you all different types of cases that you might encounter in your work. Now it's your turn to try it, so give these a shot. See me in intervention if you need help. I'll see you then.